Okay, let's get started. So, the weather is getting better, but so we will take the midterm exam 2 weeks later, right? 2 weeks later. So, the April is a beautiful month, but also you need to focus on studying, right? So, so so please be prepared for the midterm exam. So okay. So as you know, so I posted the lab assignment and the homework assignment on the Blackboard. No, LMS. So the please try to answer the homework questions by yourself. Okay. So it will be very helpful for preparing the midterm exam. Okay. And then as I mentioned, the difficulty level of the midterm exam will be similar to the difficulty level of the homework assignment. Okay, so if you can answer the homework questions by yourself, then I believe you can also answer the midterm exam questions. Okay. Also, for the lab assignment, actually in the lab assignment, you will be requested to install the cross compiler, the RISC-V cross compiler, and then you can also compile very simple C code using the cross compiler, and then you can also generate the RISC-V assembly code, right? And then also you can execute the RISC-V RISC-V instructions using the instruction set architecture simulator. Okay, it's called Spike. Okay. So actually, I believe most of you use Windows operating system that run on Intel or AMD CPUs. And the Intel or AMD CPUs use x86 ISA, right? And some of you may use the MacBook, okay, Mac operating system. So, and then recently the Apple use ARM CPU, okay? No, their own CPU, but this Apple CPU employs ARM ISA, okay? So actually the most commonly used ISA are not the RISC-V. So actually, on your computers, we cannot run RISC-V compiler directly. Okay, so because our computers run x86 or ARM ISA. Okay, so it means that we need to install cross compiler. So cross compiler means that for example, on x86 system, we can generate the RISC-V binaries using cross compiler. But so we need to build. So because our native system does not include the RISC-V compilers, right? So it means that we need to manually build RISC-V cross compiler, but don't worry about that. So actually, I provide the detailed instructions for installing the RISC-V cross compiler. So actually, you need to install this RISC-V cross compiler on Ubuntu. Okay, Ubuntu-based operating system. Okay, and I believe you can install the RISC-V cross compiler on your MacBook, but using using Brew, so it's a package manager on Mac. But so I don't know about this. Well, you can install, but I don't know about some PK. There is a proxy kernel, or I don't know about the Spike on Mac. So So actually, in the first lab assignment, I believe you can install uh, Mac users install the virtual machine, right? So virtual machine, they can run Ubuntu-based operating system. So actually on this Ubuntu Ubuntu-based virtual machine, so you can install RISC-V cross compiler, okay? And then also, if you are using Windows operating system, then you can use WSL. Okay, so you can easily install WSL on your Windows operating system, and then actually WSL is the the virtual machine for Linux. Okay, Linux operating system. So you can also install the Ubuntu applications on WSL. Okay. Okay. Then so you need to build the RISC-V cross compiler, and then also you need to build Spike RISC-V ISA simulator. Okay, so it is because so we cannot run RISC-V binaries, right? So obviously our computers use x86 or ISAs, right? So our computers cannot run RISC-V binaries. So we require simulators. So simulators can run RISC-V instructions using software. Okay, it's not hardware, but so using this software, we can just execute means that we can just emulate the execution of RISC-V instructions, right? So Spike is the RISC-V ISA simulators, right? So the problem is that our simulator does not include operating system. So which means that the binaries, so we can run binaries, the instructions, but these binaries cannot be uh, assigned. Okay, cannot be launched properly. Okay, so that's why we use proxy kernel. It's called PK, right? So also you need to build the proxy kernel of RISC-V. So it's called PK. So so the PK is the RISC-V binaries. Okay, so and then uh, uh, for the lab assignment, you need to run PK and your compiled binary. Okay, then you can run your binary file using Spike RISC-V ISA simulator. Okay, so actually for the first this lab, so you can just follow the instructions on the lab document. So if you correctly follow the instructions, then I believe you can easily complete this second lab assignment. Okay, so actually we tested this lab on Windows machine, also on Mac machine. Okay, so it properly worked. So so if you encounter some errors, then firstly, so you need to check your some your history, so like the command history, and then uh, try to find your errors, and then you please fix your commands. Okay, so actually you can copy and paste the instruction like commands on the lab document. Okay, but if you can type your these commands, then you can mistype mistype some comments, then you can encounter some errors, right? But so just to follow the instructions correctly, okay, for this lab assignment. Then I believe then I believe you can complete the this lab assignment without errors. Okay. So and then also you can just follow. You can just follow instructions. Okay, you can generate some output files, and then you can just submit your result. But for this lab assignment, try to understand. Try to understand how the high-level language code is compiled, and then how the RISC-V instructions. RISC-V instructions are generated by compilers, and then you need to understand how instructions are really executed in hardware. Okay, so we are learning. So in chapter 2, we are learning about the RISC-V instructions, right? RISC-V instruction sets, right? But you need to understand. You need to understand how these instructions are really executed by hardware. So firstly, so I mentioned that so we need to set program counter of the target instruction, right? And then using this program counter, we need to read instructions from memory, right? And then these instructions are just executed. And then in order to execute the read instructions, then we need to the, the hardware needs to decode. Okay, it's a analyze the machine instructions, right? So by doing this second lab assignment, so please try to understand how these instructions are executed. Okay, so using the Spike simulator, you can run the compiled instructions. Okay, so you can run RISC-V instructions. Also, you can run these instructions one by one, like run. Then Spike just execute only one instruction. Okay. Then also you can check the content in register file. Then also you can check how the register files are changed by instructions. Okay. So and then and then if you encounter any errors, okay, so even though you just type the build commands correctly, but if you encounter any errors, just contact our TAs. So you can get help from TAs. Okay, so you can post questions on Piazza. Okay, any question about the second lab? Okay, no. Okay, so I believe you can just follow the instructions correctly. Okay. So we are learning how to translate the RISC-V instructions, the assembly instructions into machine code. Okay. Actually, this translation is performed by encoding rules. Okay. So yeah, we learned about the R-type instruction, and the R-type instruction includes 3 register operands, and then we learned how RISC-V instructions. These R-type instructions are translated, encoded into the machine code. Okay, the machine code includes only binary numbers. Okay, and then based on these rules, that we can just encode. We can just encode the RISC-V assembly instructions. So we learned about the immediate type instructions, and then so you need to no, so we need to remember immediate type includes the 12-bit signed two's complement immediate. Okay, two's complement constant number. So you need no, this is the signed number. Okay. Okay, and then SMB type, it's a store and branch type. Okay, and then so I type includes the immediate type instructions like add I and sub and then or I. Also, it includes load instructions. Okay, and then SMB type. SMB type is the store and branch type. So I mentioned that SMB type includes two source registers, right? And one immediate. So unlike these I-type instructions, the I-type instructions include RD and then one source register, right? But in order to encode the S-type instructions, so S-type instructions or B-type instructions include two source registers. So, and then with these instructions do not use RD. So immediate number is split into two parts, and then the upper part is stored in this this field, and then the lower part is stored in this field. Okay, this is the S type, and then actually the B type has the same structure, but only immediate number. Immediate number is stored in this field with a different manner, right? So this is just a rule, okay? So because this is just the encoding rule, so you need to just memorize. But so actually during the exam, I will provide these encoding rules, right? So actually you don't need to memorize, okay? So but just to understand. So but you need to know how to encode. So how, based on these encoding rules, then you need to understand how the assembly instructions are translated into the machine instructions. Okay, but it's okay. Okay, during the exam, you don't need to memorize. Okay, I will provide this information. Okay, so as time, and then based on the encoding rules, we can just uh, put some the binary numbers to the corresponding fields, the machine code, machine instruction, and then we can generate the binary data. And then when we represent this binary data, this is too long, so we can use the hexadecimal numbers, okay? So you can also, during the lab assignment, also you can find the encoded, so the machine instructions, right? And then but you can also find that machine instructions are represented using hexadecimal number. So it is because the binary number is too long, okay? Okay, so it's a B type, but so the B type has also include two source registers and immediate number. So B type is the branch type, like the BQ, X1, X2, and label, right? But I explained that the label is actually the immediate number, right? So actually, so when we write a RISC-V assembly code, we can use the letters, like like some L1 like letters to represent the label of the target of this branch instruction. But actually, this label is translated into immediate number. Okay, and then what is this immediate number? So immediate number is the offset. So it's a difference between the PC of this PQ and the target of this branch instruction. So for example, the target of branch instruction is like so it's a L1, but L1 is the PC plus immediate, actually. The program counter of the L1 is the current PC, the program counter of this branch instruction plus immediate. And then the immediate is the two's complement number. right? So it's a signed number, okay? And then I also explained that this immediate number needs to be multiple of 2, right? So it should be even number, okay? The odd number is not allowed. So then actually, so x1 can be here, and then x2 can be here, and then immediate number needs to be allocated to the machine code fields, okay? But actually, I mentioned that the immediate number is the multiple of 2, so which means the LSB. LSB is always 0, okay? Because this is the even number, right? So what does that mean? Actually, this is the redundant information, okay? So what does that mean? Because this number is always 0, so actually we do not store this number, right? So that's why in the B-type instructions, we just store immediate number, but immediate number bit 12 down to 1, okay? So the LSB is not stored because it's always 0, right? So we don't need to store. And it is, and also it is because we need to store information in the limited field. So these fields, the machine code data is a very precious resource. Okay, so we don't need to. If we don't need to store some information, then we do not store this information in the instruction. Okay, so immediate number is stored in the machine instruction like this. Okay? This is just a rule. Okay. So, but you can find that the pin number 11 is stored here, and then the sign bit is stored here, and the 10 down to 5 is stored after the sign bit. Okay, so let's see the example. So this is the example. The risk PQ L1, and then L1 is here. So what is the offset? Offset is the difference. So difference is 16, right? So this is 70 and then 80. Okay, so difference is 17. So immediate number is just 17. No, 16. 16. Sorry. So it's a PQ, S0, T5, and 16. Okay, 16. Okay. So, and then 16 is the binary number. So if we can represent the 16 using a binary number, okay, so you know it's the 1000, okay, but and then this is the pin number 12 down to 0, okay, but in the encoding rule, so we do not use the LSB, right, just to remove LSB, the last 0. And then we can just allocate these numbers to the immediate field. Okay, so this is a sign bit. Sign bit is here, and then 11 bit, pin number 11 is here. Okay, and then the 10 down to 5 is stored here, and then 4 down to 1 is stored here. Okay, so this is how the immediate number is stored in the B-type instructions, okay? And then, so, so as I mentioned, this is just a rule, okay? So you can just follow this encoding rule, okay? And then U and J type. The U and J type, U type is the upper immediate type, like the LUI, okay, LUI instruction. So LUI instruction just to use a 12-bit immediate number. It's a 12-bit. And then jump. Jump instructions also handle 12-bit immediate numbers, right? So UNJ type instructions just instructions and the 12-bit immediate number. So this encoding rule is for this U and J type instructions. Okay, and then this is the encoding rule. OP code here, and then RD is here, and then large immediate number is here. But also, you can find that for the J type is the jump type, so immediate fields is allocated like this. Okay, so let's see the example. So LU type instruction. So LUI is the example of U type instruction, and then it has two operands, RD, and then the upper 12-bit immediate number. Okay, so we learned that we use LUI to generate very large constant number, right? Right. So we can generate a large constant number using LUI and add-I, right? So that's what we learned in the previous class, right? So it has only LUI has only two operands, RD and then immediate. So OP code is here and the RD is here, and the immediate can be stored in this field. Okay, so this is the example, but the example is very simple, right? And then J type. Okay, so it's the jump type instruction, like JAL. So JAL is the jump and link, and then so it uses one RD and then one immediate field, immediate number. But also the jump just change the program counter. So you can write the jump instruction like JAL and then not R0, JAL, where is, and then X0 and label like L1. But like the branch instruction, then actually this label is the offset, of a program counter. So it means the difference between program counter of this JAL and the target. Okay, so this is the immediate number, but this immediate number is the program counter of L1 minus the PC of this JAL. Okay, this instruction. Okay, so now this is the example. Okay, so you can find the JAL array func1, and then the program counter of this JAL is the 540C. Okay, and then what is the target? Target is the func1, and then this is the PC. So we can calculate this immediate number as the ABC04 minus 540C. Okay, then the number is A67F8, right? And this is the binary number. Okay, and then like the branch instruction, so we just remove the last zero, the RISC-V 0, because as I mentioned, this immediate number is always multiple of 2. Okay, it's an even number. Okay, so and then we can write the binary number like this, and then based on the encoding rule, then we can just allocate these binary numbers. The first bit is the sign bit, and then it's a 10 down to 1. It's somewhat ridiculous, but it's just the encoding rule. Okay, you can just make the machine instructions based on the encoding rule. So actually, this encoding rule is designed based on the hardware consideration. So it means, okay, so actually the machine code is given to the CPU, then CPU first decode. Decode is the reverse process of encoding, right? So it means it analyzes the machine instructions, and then it identify which instruction is given. Okay. Then the immediate number is also identified. Okay. And then this immediate number is used for generating the program counter, so target values. So then by considering the hardware structure, this encoding rule is designed. Okay. But you can just memorize this. Okay. But don't worry about that. So I will provide this encoding information. Okay, this is the summary. So we learned about the 6 types of RISC-V instructions. Okay, the R type, I type, and then U type and J type. And then this is the instruction format summary. So actually, I will provide this figure to during the exam. Okay, okay. So, but you can find some regular location. So it's a common encoding rule for these instructions, right? So what are common rules? The lower 7 bits are used for OP code, okay? And then usually the next 5 bits are used for RD. And then RS1 is here, or RS2 is here. And then we fill the immediate numbers and or the function code, function fields for the remaining fields. Okay. So when we design the encoding rules, then actually we just used some regular encoding rules. Okay. So it means the field, we use the common fields for some common operands or common OP code. Okay, so OP code is always occupy the lower 7 bits of the machine code, and then RD is usually here if RD exists, and then if RS1 is here, RS2 is here, and then we just allocate immediate or function fields. Okay, this is the encoding rule. Okay, right? So this is simple. So good design demands good compromises. Okay, we can, so as I mentioned, we can apply some common rules for this instruction encoding, but we can just also allow some compromises. Okay. Okay. So then let's see how hardware decode instructions. Okay. So if machine instructions are given to the CPU, right? So this is the machine instruction. It's a 32-bit binary data. Okay. Then CPU needs to decode. Okay. So I mentioned that decode is the inverse process of encoding. So which means the CPU needs to, so based on this machine instructions, CPU needs to identify the type of instruction, like, oh, this is the R type or I type. Also, CPU needs to identify source registers or destination registers, or if required, immediate numbers, and so on, right? So this is the inverse process. Based on the RISC-V assembly instructions, we generate the 32-bit binary data. It's a machine instructions. And then based on the machine instructions, a CPU needs to identify this instruction, right? So assembly instruction, right? Then how? So firstly, a CPU needs to check OP code. Okay, so based on the OP code, we can know, oh, this is the R type instruction, or okay, oh, this is the I type instruction, or some like load type, or store type, print type, blah, blah, blah. So firstly, we CPU checks the opcode field. Then this CPU can identify the types of instructions. Then based on the instruction types, then by reading the corresponding field, the CPU can identify RD or immediate numbers or RS, the source registers. Do you understand? So let's see the example. So this is the machine instruction. Okay. So this instruction, this data. So using the program counter, CPU reads this data from memory, right? So this data is given to the CPU. So this is the just binary data. And then this is the hexadecimal number. So we can write the binary data like this. Okay. Then based on the this table, okay. So we know that the lower 7 bits are OP codes. Okay, so OP code is 0. The first CPU first read this OP code. Okay, so then this OP code is the 5-1. Okay, 0x51. So which means it's the R type instruction. Okay, then this is the R type instruction. Then CPU can identify, this field is used for RD, this field is used for RS1, this field is RS2. Okay. So, and then also it needs to identify the operation of this R type instruction. So, and then it reads the function 3, and then if the function 3 is 0, then it's add or serve, and then if the reads the function 7, and then it's the sub, right? And then by reading this field, this is the RD, and then also this is the, what is this? This is the RS2, and then this is the RS1. Okay. So, right. So decoding is the inverse of the encoding. Okay. So the CPU can identify instructions like this. This is another example. Also, firstly, read the OP code. So if the OP code is the 19, then this is the I type instruction. Then also in this the function 3. And if the function 3 is 0, this is the add I. And then mm, mm, oops. Then function 3, then it's add I. Then it can read the RD field and immediate field, right? Okay. So this is another example. So, and then, okay, so not another example, it's the same example. And then if we know the type of instruction, then we can just apply this encoding rule or an encoding and decoding rule, and then we can get the required information for identifying the RISC-V instruction. Okay? So why did I explain this? So because in chapter 4, we will learn about the hardware, the hardware architecture of the RISC-V CPU, which means you need to understand how the instructions are executed. instructions are rarely executed in the RISC-V hardware. Then, firstly, we need to decode. So using this input binary instructions, okay, input machine instructions, the CPU needs to decode. So the CPU needs to identify the assembly instruction from this binary instruction. So we can apply, so the CPU can apply the encoding rule. So encoding and decoding rule, because decoding rule is the inverse of encoding rule. Then the CPUs can extract the required information from this binary instruction, the binary code. Then it means the hardware performs this process, okay? Which means we need to design the hardware that can perform this decoding, okay? Instruction decoding, okay? That's why I explained about this process. Okay, this is the summary of RISC-V instructions. So I made this table. Oh, this you can find that this is the category of the instructions, and then you can also find the format of instructions, and then you can find that this is the I type, S type, R type, I type. That's what we learned. Okay, so we learned about the encoding rules like the R type, I type. So you can also find the format of instructions. So S type, R type, I type, R type, I type. So it is because arithmetic instructions or the logical instruction or shift instruction has the R-type instructions and I-type instructions, arithmetic, logical, okay, and also compare instruction. These instructions have both R-type and I-type instructions, okay? That's why it's RI, RI, RI. Also some instructions like LUI, so this is the U-type instruction, okay? And then also you can find the branch instruction and jump instructions. SB, so it means the branch is B type instruction, and then UJ represent the jump type instructions. And then also you can find that, OP code. You can find the OP code of these instructions. So for example, for load instructions, the OP code of load instruction is 000011. So what does that mean? If a CPU checks the OP code field, and then if the OP code field is 000011, then CPU can identify, this instruction is load instructions. So even though the load and the shift I has the same I format, but you can find that the OP code is different. Okay, so it is because this class of instructions is different. Okay, so also for the arithmetic instruction like the add I, so its OP code is 001 0011, and then if the add instruction is the R time instruction, then we use the OP code field as the 011 0011. Okay, and then for these instructions, shift, arithmetic, or logical and compare instructions, you can find that if these instructions are R-type instructions, then OP code field is the 011 0011. And then if we use the I-type instructions for shift, arithmetic, logical, and compare, then OP code field is 001 001 0011, right? Then after that, we can just check the function 3 and then function 7 field. Then if the OP code field is 011 0011, then it is the R-type instruction of shift, arithmetic, logical, and compare. Then using the function 3 and function 7 field, we can identify, oh, this is the SLL, oh, this is the add, this is exclusive OR. Okay? I-type instruction is the same. If the opcode field is 001, 0011, then it means, oh, this instruction is the I-type instructions of shift, arithmetic, logical, and compare. Then using the functions 3 field, then we can identify the instruction. So actually this is the, actually I-type instruction do not use the function 7 field, okay? So just ignore this one. Oh, no. Actually, but shift instruction is different because the shift for the shift instructions, so we can just use the only the 5-bit constant, 5-bit immediate number, 5-bit constant number. So actually, function 3, 7 fields are all zeros. Okay. And then so you can find the exclusive or I, and then the add I. Then you can find that the function 7 does not have any values. The shift instruction is a somewhat special because actually we the shift instructions can only have the limited range of the immediate number. Okay, and then only the positive number. Also, if you check the branch instruction, the branch instructions has the same opcode field, okay, like 110011, and then jump and link has the 110111, and then jump and link and register 1100111. Okay, so that's why. So if you see this instruction instruction format table, then you can find the why. Why we need to firstly check the opcode first, and then we can identify the type of instructions, and then we can extract other fields based on the category or class of instructions. Do you understand? So the hardware just performs this operation for instruction decoding. Okay, so this is some address mode. The address mode of RISC-V, so which means it represents the operand type of RISC-V. So we can use the immediate addressing, or we can also use the register addressing. So we can generate the memory address using the RS1 plus immediate number. So source register plus immediate number. Okay. And then we can also use the PC relative address. So it means that the program counter value can be calculated using PC plus immediate number. Okay, this is summary of addressing, and then this is the summary of the RISC-V instructions. So if required, so also I will provide this information during the exam, which means actually you don't need to memorize, okay? But you need to understand how the instructions are executed and how the instructions are encoded or decoded, okay, based on this table, okay? Okay, this is the end of chapter 2, and then, okay, I will briefly explain about the x86 because the x86 is the most popular ISA, okay? So the most personal computers use the x86 ISA, okay? But recently, the mobile devices such as smartphones or MacBooks use the ARM ISA, okay? But the high performance servers or high performance computers use x86 ISA. Okay, the x86 ISA has very long history. Okay, like so the Intel just Intel made the 8080, so it's the 8-bit microprocessor, okay, in 1974. So so this is the 8-bit computer, okay. So you cannot imagine about this 8-bit computer, but actually, so this is the very simple, the very first commercial computer developed by Intel, okay, and then it's a very old computer, old CPU. Okay. And then 8086. So this is a 16-bit extension of 8080. And then this is so maybe the start of the x86 ISA. So, this is the complex instruction set. So as I mentioned, the x86 is the CISC type ISA. And then Intel also developed the 8087 is the floating point coprocessor. So actually in this course, we are learning about the integer instructions, but we know that actually we can use floating point numbers, right? So without any hesitation. So, but no, old computers, the floating point numbers were very complex, and then it required a very complex hardware. So Intel just made the floating point coprocessor. Okay, it's a coprocessor. Okay? So you may not understand this because so actually the floating point is very popular, right? But actually in this time, the hardware, floating point hardware, so it's still complex, but the transistors were very large, so it was not easy to make some complex hardware. Okay, and then 8286 is it used the 24-bit address. Okay, then memory management unit. 8386, it's the 32-bit extension. It's the 32-bit ISA for x86. It's a 32-bit computer. Okay, so 8386. Okay, it is called the IA32. It's the basic x86 architecture for 32-bit computers. So IA represents the Intel architecture. Intel architecture 32. Okay, so this is the baseline x86 instruction set, IA32. So I486 is it's a pipeline, on-chip cache, and floating point unit it includes. Okay, so it's a very basic components in CPU, but so actually the pipeline, on-chip cache, FPU are included in I486, and then Pentium. Oh, it has the 64-bit data path. And then it's the Pentium processor has the modern architecture, of the CPU actually. Okay, but it is infamous F divide bug Pentium processor. Okay, Pentium Pro, and then Pentium 2, and then Pentium 4. It's a new architecture. So Pentium 4 is the very revolutionary CPU, and then it has the newer microarchitecture. Okay, and then also you can find that new instructions. New instructions are included again and again for the different architectures of the Intel x86. Then, but for the 64-bit computers, the actually AMD uh, designed the extended architecture for 64-bit computer. So the most computers we are using today are 64-bit computers. Okay, because using the 32-bit computers, we can just use the maximum 4 gigabyte of memory. Why? So So in this course, we are learning about the 32-bit ISA. What's the problem? In order to generate addresses, we can only use 32-bit data. What's the problem? The maximum size supported by this 32-bit address is 4 gigabyte. Because, so we use the byte address, and then using the 32-bit address, we can only represent 4 gigabyte of the memory space. So it's just small, right? So AMD just proposed the AMD 64. This is the 64-bit ISA, the extended ISA based on the IA32, right? Intel architecture 32. But Intel declined to follow. It means instead, Intel developed the IA64. But this IA64 has very different instruction set architectures. Like, so if you are interested in, I believe some of you heard about the Itanium. So it's the very new processor developed by Intel, but Intel just applies the IA64, Intel architecture 64 for this Itanium processor. Problem is, it's not compatible with the IA32 existing x86 instructions. So Intel declined to follow, and then they developed the new architecture, IA64, but it was not selected by market. So we are using AMD 64 now, okay? That's why if you use the Linux operating system, then you can find that the architecture, when we represent the architecture of the CPU, then you can find that, oh, this architecture is the AMD 64. So it is because the most CPUs currently use the AMD 64. This is the extension of IA32 x86 ISA. So actually the most x86 CPUs support the AMD 64 now. Intel failed. Okay, so it is because backward compatibility is it's very important. What is backward compatibility? It means, so the Intel has developed a new architecture, and then also Intel added the new instructions. And then backward compatibility means that even though we're using this new architecture, new CPUs, these CPUs can run old binaries developed by these old architectures. Okay, this is the backward compatibility. Okay, so which means, oh, I generate this binary code in 1989 using the 486 processor, but this binary also needs to can be executed by Pentium 4, also i7, the was latest processor by Intel. Okay, so this is the backward compatibility. Okay, so but problem is that in IA64, so Intel ignores the backward compatibility. And problem is that, so this is the very good processor. Okay, this is a revolutionary. It has the revolutionary architecture, and then also it's a clean, and then it's a good, but it was not selected by market. Okay, so technology elegance is not market success. So this is some lesson from Intel. Okay, Intel IA64. Okay, and then compatibility is so critical. Okay, so this is the Intel x86 registers, and then also Intel also has some different type of operands like register, memory. So which means the memory can be directly accessed by arithmetic instructions. So that's why the Intel x86 ISA is called the CISC type ISA. Okay, so in the RISC type ISA, such as RISC-V, does not support the direct access by arithmetic instructions, right? So memory can be accessed by memory instructions, such as load or store instructions, right? So, but Intel x86 supports the direct access by arithmetic instructions, right? But you may think that also the problem is that encoding, the encoding rule is also very complex. And then the size of instruction is also different. Okay. So we learned that in the RISC type instruction, in the RISC-V, the size of instruction is 4 byte. Okay. And then so RISC-V supports the reduced type instruction. And then this type of instructions has 2 byte size. Okay. But x86 is a variable length needs to support the variable length encoding. What's the problem? Hardware becomes very complex. Also, encoding, decoding rules are very, very complex. Okay, so this is the problem. Okay, also, in order to support the very complex instruction like this, the hardware becomes very complex. So this is some disadvantages of CISC type instructions. Okay, then you may think, oh, x86 is not good. Intel CPUs are not good. But actually, Intel also changes the design strategies. So which means actually complex instructions. So CISC type instructions are translated into multiple simple instructions like RISC type instructions. Oops. So do you understand? So actually, you can think, oh, x86 is very complex. And then, as I mentioned, in order to support these very complex instructions, we require very complex decoder and then very complex hardware. Actually, it's not good. It's not good for the performance. Okay, but actually, the Intel CPUs translate complex instructions into multiple very simple instructions like RISC type instructions inside of hardware. Also, the Intel has they support the microcode ROM. So these instructions are translated, and then simple instructions are just executed by hardware, like RISC. So actually, tradition. Someone say that, oh, CISC is not good, and CISC is not good for hardware design, and it's not good. But anyway, actually, the most CPU employs RISC-like architecture. RISC. Okay, so that's why. So currently, the performance of CPUs is very high. Okay, it's good. Even though these CPUs use the CISC type instructions. Okay. Well, this is the market shares make the okay. The micro engine similar to RISC, and then also comparable performance to RISC. So even though CISC handles the very complex instructions, the performance is very similar to RISC. Is it because it it handles inside of the hardware, it handles the only simple instructions. Okay. Okay, so concluding remark. So we learned about the RISC-V instruction, and then actually, even though we use the the specific type of ISA like RISC-V, but the other RISC type instructions such as ARM or MIPS, actually these instructions have the similar structure, a similar uh, strategies or similar philosophy, okay, or similar design for these instruction architectures. So you can read the ARM architectures, ARM ISA document, but you can find that, oh, you know, obviously the encoding rule is different, right? So, when the ARM assembly instructions are encoded to the machine instructions, then the encoding rules are different, right? It's different from the RISC-V encoding rules. But the types, like the alt type, I type, or some load type, store type, and then some design policy. Design policies are very similar, okay? ARM also supports the 32-bit instructions. The size of instructions is 32-bit. And then also ARM supports the reduced type instruction like thumb. And then these instructions occupy 2 byte. Okay. So actually for RISC, also MIPS is similar. Okay. So okay, the design policy is similar. Okay. So we learned about the compiler, assembler, and some hardware encoding. Okay. So, and then I believe everyone can understand this RISC type instructions. Okay. And then as I briefly explain about the the CISC type ISA, but you can just understand that even though these CPUs support the CISC type ISA, the inside of the hardware, the the hardware just employs the RISC-like structure. Okay, so that's why the performance is similar to the RISC type CPUs. Okay. Okay, then the next chapter. Okay, next chapter. So we will learn about in the chapter 3. We will learn about the arithmetic hardware and then the number systems. Actually, in the digital logic design course, so we learned about the number systems. But in chapter 3, we will learn about the floating point number systems. Okay, not integer number systems. So we already learned about the integer number systems, and then arithmetic. So the arithmetic means that it is the addition, subtraction, and multiplication and division operations. And then actually, the RISC-V supports these instructions, right? So which means hardware. Hardware needs to include the hardware engines that can support these arithmetic instructions. Okay. But actually, in digital logic design course, we learned about the arithmetic hardware, right? Like adder and subtractor, and then multiplier or divider. Okay. Addition is very simple, right? So integer addition is very simple. Okay. So actually, but we know that actually these hardware, these engines handle two complement numbers, but like the decimal addition or decimal subtraction, we can just perform the binary addition or binary subtraction, right? So we can implement the adder, and subtraction is the addition, right? We can just invert the sign of the one other operand, then we can just perform the addition. Okay, so subtraction is very simple. Okay, so and then okay, so I'll stop here. Don't worry about that. So in the next class, we'll learn about the multiplier and divider and then floating point numbers. Okay. So, the chapter 3 is very short. Okay. So actually, and then we'll learn about the hardware. Okay. Okay. Thank you for your attention. Then see you in the next class. 감사합니다.